thank you very much for inviting me to this really great conference. I'm going to talk to you about the earliest part of Earth history and the difficulty we have with distinguishing between biogenic and abiogenic structures. If you look at Earth history, this is here now shown in billions of years. If we look at the earliest part, the Hadean, the first 500 million years, there's basically nothing we know about this, simply because we don't have a rock record. But there were some very important events. The moon formed, the first oceans formed, and we had a late heavy bombardment. So we had a lot of meteorite flux here. And very important to note is that didn't really stop after the heavy bombardment. We have evidence in rocks that are 3.5 billion years old that there have been major impacts. This is really important because some of these impacts might have had a sterilizing effect on the Earth. So what could have happened is that Earth originated, evolved, and then was completely wiped out again simply because the oceans boiled off during a major event that happened, for instance, 3.5 billion years ago. So that's something to keep in mind, that life might have actually originated and evolved several times. But we don't know anything here. We just have assumptions. However, later in Earth history, we have another major event. This is basically the biggest event in Earth history. It's the oxygenation of the Earth's atmosphere. Very important moment, 2.5 billion years ago, that triggered a whole suite of other events that are listed here. And one thing that is important for life is that we think for sure that life was present here, simply because oxygen in the atmosphere was very likely produced by oxygenic photosynthesis. So most people agree that here life was not only just present, but was actually dominant on the surface of the Earth. So what happened between these two major episodes? This is basically a billion years here, where we have a very patchy rock record, and everything we have has been highly metamorphosed. So if we look at traces, for instance, biomarkers, molecular fossils, so molecules we can extract from organic cell walls of microorganisms. Here's an example of a microbialite in Yellowstone National Park. We extract these biomarkers, and then we can see certain biomarkers for a specific group of organisms and trace it through the rock record. I pointed here at 2.7. Beyond that age, approximately, it becomes really difficult to identify biomarkers, simply because the rocks that are older have been metamorphosed, have been exposed to temperatures and pressures that would have altered these structures towards macromolecular material that we call kerogen. So extremely difficult to identify biomarkers in older rocks. But we do have all this organic material. We have all kinds of microstructures that we see in the rock record, and we can still extract information from that. For instance, isotopic ratios. We have a carbon isotope record that goes all the way down, intriguingly, to the oldest rocks on Earth. And I'm going to show you some of the controversy about that. We also have other indicators, other isotopic ratios, sulfur isotopes, nitrogen isotopes. We have elemental ratios, nitrogen carbon, phosphorus carbon, sulfur carbon, the elements that are important in biologic processes. And so there's lots of controversy about when we can actually use that as a real trace of life. And then we have all kinds of interesting structures that we see in the rock record. It has been mentioned already in earlier talks this week. We have so-called stromatolite structures formed by microbial mats that have been growing towards the light and have been trapping minerals and precipitating minerals. And what you end up with are growth structures, laminar growth structures, that we can trace all the way down to about 3.5 billion years. And then, of course, well, just to quickly mention, the fundamental problem with these structures is that it's really difficult to find microfossil structures in these kind of stromatolite that we find in early rocks. However, we do have a lot of organic microfossils that we see in all kinds of chemical sediments. The most important of these are chert deposits, chemical precipitates of silicon oxide, so ultimately turning into quartz. And then you get these kind of quartz-rich rocks that preserve these kind of organic structures. And there's an entire record that goes down to at least 3.5 billion years ago, and even in older rocks. The problem is, however, that all this material, all organic material, has been subjected to pressure and temperature in these rocks. And what happened, as I mentioned earlier, is functional organic molecules have turned into a macromolecular structure, kerogen basically. And this is what happened when rocks are subjected to pressure and temperature. The organic material loses functional groups, it loses heteroatoms, and actually isotopic ratios are also affected. Ultimately, we get graphitization, and we end up with a pure crystalline structure, which is graphite. So many of these organic microfossils that we see in these early rocks are graphite. They're graphite particles. So we end up with three fundamental problems when we try to reconstruct early life. We have a morphology problem because most of these organisms were extremely simple in form. Most of them were filaments or rod-shaped, and unfortunately there are many abiologic processes in nature that generate exactly the kind of shapes that we see in microbial forms. The other fundamental problem is that most people agree that the most likely site for the origin and early evolution of life was in hydrothermal settings. The early Earth was ultramafic, and it was already pointed out yesterday, water-rock interaction with ultramafic rocks leads to serpentinization and lots of possibilities for hydrothermal activity. The problem is, those are the sites for prebiotic chemistry and abiotic chemistry. They're also the sites for primitive life. So you have a problem here, you have a double problem. If you want to study prebiotic chemistry, life is in the way. And if you want to study life, prebiotic chemistry and abiotic chemistry is in the way. So this is a fundamental problem. These are the most difficult sites to study, actually. And then, of course, metamorphism, as I pointed out. So here are the fundamental questions you need to ask yourself when you find an organic microstructure in an ancient rock. Is the structure actually part of the rock? Or is it a microorganism that simply crawled into an old rock? There are many controversies that are actually based on that problem. Is the structure, organic structure, syngenetic? Did it form when the rock formed? There are many organic structures that are part of a rock, but did not form when the rock formed. I'm going to show examples of that. These are metamorphically induced structures. And certain abiologic processes related to hydrothermal settings are so-called Fischer-Tropsch type synthesis, for instance. Can we exclude these based on geologic reasoning? And of course, ultimately, can we have additional information that we can link to the morphology? Can we study the microstructures themselves and look at the chemistry, isotopic ratio, and structural characteristics? In the end, we need to link the microstructures with the geologic context. And for that, it's critical to have analytical methods that are in situ and operate at a very high resolution. And this is exactly what people have been doing recently. There's all these techniques that I'll briefly point out that we can apply to actually characterize these kind of structures. We can look at chemical composition, elemental composition. We can look at degree of graphitization. I'll give examples of that. And we can do all kinds of isotopic studies on these structures. So I'll run quickly through the techniques. We've seen several talks already on Raman Spectroscopy, a very important technique. It identifies organic material as being organic, and it gives you an indication of the degree of structure. Pure crystalline graphite has only one band in the Raman spectrum, this G band here, stands for graphite. And if there's dislocations in the graphite structure, you get a disorder band, and several disorder bands. And the more dislocations you have, and the more disordered the material is, the more of these disorder bands start to appear. So here you see three different rocks that have been exposed to different degrees of temperature. Actually, Barman's a bit higher. Iswa is about 550 degrees. And you see that there's a progression in these disorder bands. Basically, there's a lot of disorder bands in poorly altered material, and then they start to disappear when you go to higher degrees of metamorphism. And note this band here, this becomes a prominent band, this D1 band, but when you go from about 300 degrees to 500 and even higher degrees of alteration, you start to progressively lose this disorder band because dislocations disappear. This is very important, and people have used all kinds of ratios of these bands to link them to maximum temperatures of alteration, so-called geothermometers. And then, of course, what we can do, we can scan over a rock thin section and make many Raman spectra, and we can create hyperspectral maps. Here are some examples of this. This is a hyperspectral map of kerogen that occurs in a carbonate crystal. This is from the Dresser Formation in Western Australia. And we see organics sitting in the crystal, but also in the growth zones. Now, of course, these growth zones, they formed later, and we can actually see that there's a difference in degree of structure between this kerogen and the kerogen that was added at a later stage. So it's very useful, this technique, to identify degrees of alteration. Very important to note, it's not a biomarker. The Raman spectrum does not work as an identification of life because there's many abiologic structures and also lots of artificial structures. Graphene, carbon nanotubes, all kinds of material that also has this spectrum. So you have to be very careful. We can shoot holes in the thin section with an ion probe. Here you see a tiny hole, and the material in this hole was blasted out, turned into a plasma, and measured with a mass spectrometer. When you do that, you can make in situ isotope analysis, for instance. And then a technique that has very recently become very popular now for this field of science, micropaleontology. This is coming from material sciences, basically, where you use a focused ion beam mill to mill out an extremely thin foil out of a rock thin section and lift it out and put it under a transmission electron microscope, and then you can zoom in at extremely high resolution and start to study on a nanoscale potential traces of life. This is a study Lapland et al. We published last year. This is an apatite crystal from the oldest phosphorite on Earth, 2 billion years old, and inside the crystal we see all kinds of little circular structures that are interpreted as being remnants of methanogenic microorganisms. So let's go to some of the controversies. We go to the oldest part of the rock record. The oldest rocks that we think are sedimentary are about 3.9 billion years old. They occur in western Greenland and on the coast of eastern Canada, and they are highly, highly metamorphosed. This rock has seen, this is granulite facies metamorphism, it has seen temperatures of 7 kilobar, 700 degrees Celsius. And in this rock, people have identified graphite particles inside apatite crystals, actually. This is not mentioned here, but this is Moschitz et al., 1996, Nature. And it was argued that these graphitic particles are the remnants of microorganisms that have been completely altered. But if you go into the rock and you study these graphite particles, there's a problem. And that's the following. This is a study by Lapland et al. If you go into these thin sections, and you zoom in and you go there with a Raman spectrometer, you actually see that there are fluid inclusion trails running through these rocks. Now, fluid inclusion trails, they form typically during metamorphism. And inside the inclusions, we find graphite. And there's two important conclusions here. One, that graphite sits in fluid inclusion trails. That means that it formed at a later stage. It did not form in rock form. That's epigenetic. And the second conclusion is there's this D band in the Raman spectra. It's disordered material. And at this degree of metamorphism, we should not see that. If organic material was present initially, it should have altered to pure crystalline graphite, and it didn't. So this formed at a later stage after the main metamorphic event. If you then look at what is else in these fluid inclusions, CO2 mostly, but also sometimes methane, you can actually run through the thermodynamics of this. This is a COH ternary diagram of the phase relations between graphite and a carbon-bearing fluid. And there are several ways in which you can generate graphite from a fluid that has these compositions. So if you have CO2, methane, and water, you can dehydrate the rock, for instance, by forming hydrated minerals, and then you move your fluid composition into the graphite stability field and you start to precipitate graphite. You can do the same by lowering the temperature, so during a retrograde metamorphic event. And then, if you look at these graphitic particles inside apatite, it turns out they're not inside apatite. They're on the surface of apatite crystals, and it's just actually part of fluid inclusion trails. So, we have graphite in this rock, but it's epigenetic. It did not, it formed at a later stage. So, we go to slightly younger rocks here, the Isra supercrustal belt, 3.8 billion years ago. Slightly less metamorphic grade. amphibolite facies, 550 degrees Celsius, 5 kilobar. And also there, graphite was found in apatite crystals, but it was found in what then were thought to be sedimentary rocks, carbonate deposits. But if you look closely at these rocks, and I go to the next slide here, we see that these are veins actually. And they've been reinterpreted as being metasomatic carbonate veins, rocks that formed during a metamorphic event. And when you look at the petrology, you see that graphite, and in this case graphite is actually sitting in the apatite, but it's sitting everywhere, associated with siderite and magnetite. Siderite is an iron carbonate, and when you bring siderite up to about 550 degrees Celsius and 5 kilobar, you get this reaction here. You get a siderite disproportionation reaction, and it actually turns into magnetite and graphite. People have done this in the lab. So this petrographic association here suggests a completely secondary metamorphic process. A recent study by Otomo et al., however, found graphite in rocks that are not carbonate deposits. Earlier this was also shown by Rosing et al., but this recent study actually did this high-resolution TEM analysis, and what they saw is that the graphite in this rock is not pure crystalline graphite, but on a nanoscale has these little wiggly structures here. And it has been argued that this might be because the precursor material was very complex, like a biologic mineral, and that a biologic graphite would never make these kind of structures. This remains to be seen by experimental studies in the future, if this is a biomarker actually. So I go to younger rocks, 3.5 billion years ago, and I'll discuss briefly probably one of the most famous controversies that we have. Many of you probably have seen this, but I'll run through it because it's such an important example. This is the Apex Chert in Western Australia, and in this rock here, which was interpreted as a sedimentary stratiform chert deposit, these structures were found. And initially they have been argued to be the remnants of cyanobacteria, filamentous microorganisms. Later a paper was written by Schopf et al. Showing also the Raman spectrum of these structures. And it was claimed that these are Earth's earliest fossils. Intriguingly, in exactly the same issue of Nature, Brasher et al. Showed exactly the same structures from exactly the same rock with exactly the same Raman spectra, arguing for a biologic origin of these structures. And there are several arguments, but the most important argument is these structures were not found in the stratiform part of this chert, but in this part here, which is a feeder dike. It's a deposit that forms from circulating hydrothermal fluids, not from a sediment that was forming on the bottom of a sea. And that is critical important here, the geologic context, because it means that you have now a hydrothermal system in which it is possible to have abiologic reactions. And of course, then they started arguing for that. This is a later paper of Brasher et al., where they show that Fischer-Tropsch type synthesis in such a system would generate organic material, and that organic material can then get trapped between nucleating and crystallizing quartz particles in this chert. And then you get all kinds of wiggly structures that ultimately look like microorganism filaments. And then a very important study by Garcia-Revés et al. Showed that you can just make this in the lab. If you just mimic an alkaline hydrothermal solution that is supersaturated with silica and carbonate, you actually start to make self-assembled crystal structures that very much look like organisms, and they can absorb, of course, organics that are made by Fischer-Tropsch, and then you make this with exactly the same Raman spectrum. So there's problems here. We have abiologic processes that actually mimic every aspect of an ancient trace of life. And basically that's summarized here again. The problem is this, that we have sediments, but we have often those sediments related with hydrothermal feeder dikes, hydrothermal settings. And the question is, are we looking at organisms that fell into this sediment, or are we looking at Fischer-Tropsch type synthesis from a hydrothermal setting? Or, third possibility, did we have actually traces of microorganisms that live in such a hydrothermal setting, such as chemolith or autotrophs? So we have three fundamental problems here, or we have three things between which we cannot distinguish at the moment. A recent study, that we recently did. There are several others who found the same thing. Actually, if you compare this part to that part in the apex chert, and you look at the organics, then there's a subtle difference between the Raman spectra. The D4 band is a bit higher in material that comes from here than material that comes from there. And we don't know at the moment if this is due to different degrees of alteration, that these hydrothermal fluids alter the material more here, or that it's related to a precursor material. So let's go to a stratiform chert. So now we go to the Barberton Greenstone Belt, 3.4 to 3.2 billion years ago. Here's an example of such a sedimentary chert. It's overturned, as you can see, and here you have the sea floor with all these pillow lava structures here, and this is this sediment here. If you look, there's many of these sediments in Barberton, and if you look into them, you see these organic structures, and several studies have been made by many people. Here's just an example that I show from an earlier study I did, where we used ion probe analysis to show that organic material in these rocks still contains some nitrogen in its organic structure and also has a very low delta C13 ratio. The problem is, many of these rocks have organic veins running through them. And if you look at these organic veins, they also have these low delta C13 values. And I've argued in this paper that this is migrated organic material, so bitumen. Because remember, when you bring rocks through the early stages of metamorphism, so diagenesis and then metamorphism, you push a rock through the oil window. So you actually make oil, and you can make bitumen that flows through these rocks. Could be biologic in origin, but the problem is it has been migrated. So we don't know the actual source. We have not much information about the type of life. And we actually don't know if it's coming from a rock that's younger than the rock it's actually sitting in. So much better are studies like this. This is Javot et al., who studied slightly younger rocks in the Moody's group. This is a picture top down in the sediment. This is a picture front on the sedimentation, the layering of the sediments basically. And what you see here are these kind of organic structures that when you see them face on are completely flattened. And this is a very important indicator for syngenicity. These structures must have been present when the rock formed. They're not migrated because they were flattened when the rock was flattened. The entire sediment was compacted, and so were these structures. So this is a very interesting trace of life. It's at least syngenetic. Well, this is not syngenetic. And since then, many people have been doing all kinds of detailed in situ analytical studies on a whole suite of organic structures that we've been finding in rocks of that age. This is now Australia again. This is the Strelly Pool Formation. We find structures where people think they have remnants of cell wall structure. And there's actually whole communities of different morphologies that we find. These are studies by Subitani et al. And of course, what people are now doing is combining all these in situ analytical techniques to completely characterize these kind of structures. This is a study by Lepault et al. Here they look at, again, these structures that are found in the Strelly Pool Formation. And they combined all these in situ analytical techniques to show that certain structures have certain delta C13 values, have certain H to C ratios, have sometimes preservation of lipids, question mark, and that sometimes we see differences in Raman spectra between these structures in the same rock. So there's now many possibilities to better characterize all these organic microstructures. That brings me to my almost my last slide here. I've shown you some of the problems, basically, especially in the earliest part of the rock record. And I've shown you that later on in the Archean we have very good evidence for traces of life, and that we're getting better now in the description of traces of life in the oldest part of the record to about 3.5 billion years ago. A last important remark is, of course, that here we start to lose our history, basically. We really don't know anything beyond about 3.9 billion years ago. We don't have a rock record. On Mars, we know that there were habitable conditions at that time. We also know that after the Hesperian, approximately, Mars was not a geological active planet anymore. So the part that's missing here might actually be nicely preserved on the surface of Mars. And therefore, it's extremely important to go study that surface. Okay, well, some last remarks. These are some of the people I've been working with. Thank you very much.